Okay, as you might have realized, studying the forces can get a little bit confusing when we have all these interactions happening. So what we often do is we draw what are called free body diagrams on a single object so we can focus on the forces that are impacting that specific object. So free body diagrams show all the forces acting on a specific object. And we draw that object as either a box or a dot, simply to make it simple because not everyone's a good artist and some of the objects can be really complex, and it just makes it much easier to observe those objects as boxes or dots. Arrows represent forces pointing away from the object, and the size of the arrow is used to represent the magnitude of the force. So a larger arrow is for a larger force. If we're looking at this is a decent example of a free body diagram or a force diagram. There are 5 main types of forces that we're going to focus on. The F-app, with the subscript app, is the applied force caused by an outside factor, such as a person. F-tense, or just F-T, is going to be a tension force caused by a rope or a chain or a string. F is the friction force, so it opposes the motion of an object. Fn is the normal force. This happens when an object is in contact with a surface and it is always perpendicular to that surface. Okay. So it was kind of like when Snoopy was sitting on the floor and we had that reaction force. His weight is pulling down, of course, but the floor is also pushing up. In that case, since the surface was the floor, that force was the normal force. And Fg, the force of gravity, the gravitational force, is always present and always straight down from the center of the object. So next we're going to go over some examples. Let's say we have a mass at rest. Okay, so if it's at rest, that means we have no velocity, we have no acceleration. So be aware, this also means that the net force acting on this object is 0. Okay? We're going to assume that this line is some type of surface, whether it's the floor or a table, it doesn't really matter, but there is a surface. Okay? Our first force is going to be the force of gravity, and it's always pointing down. Next, since it is on a surface, we do have what's called that normal force, because the object is not falling through this, there's no acceleration down, we have to have that opposite force pointing up. Notice it is equal and opposite. So that means that both of these forces will cancel out to have a net force of 0. This one is slightly more complicated because now we are accelerating to the right. It doesn't specify why we're accelerating, but we know we're accelerating to the right. Okay? We are still going to have our force of gravity pointing down because it's always there. We're still on a surface, so we are going to have the normal force pushing or going up. And since it doesn't mention that the mass is being lifted or falling, that means the normal force and the gravitational force are going to be equal and opposite. Now, since the mass is accelerating to the right, we do have motion in the right. And because we have motion, we are also going to have a force of friction to the left. Now notice I made the friction vector smaller than the applied vector. And the reason that is because it does say that it's accelerating to the right. If it was of equal size, I would understand that there was motion occurring because we do have friction. However, that would assume that there's no net velocity, which means it would probably be at constant velocity. Sorry, no net force, which means no acceleration, which means constant velocity. We do have, or we can have, angles when we're talking about forces. We're still going to have the force of gravity down. We're still going to have our normal force up. And our friction force, assuming it's in motion, is still going to be opposing the motion to the right. Now if we have something hanging, we're still going to have gravity pulling down, but we don't have a normal force because there is no surface that the object is resting on. Instead, we have what's called a force of tension, that tension force. We're assuming there's some kind of rope or chain or something holding the object in the air. And since there's two of them, that means there are two tension forces. Okay. For example, what is the tension, Ft, in the rope below if the block accelerates upward at 4 meters per second squared? Draw and sketch the free body diagram. I'm going to walk through this one with you because it is a little bit challenging. So we're lifting a box or a block upward with a rope, and it's going to accelerate at a rate of 4 meters per second squared. Okay, so first thing we want to do is figure out what the free body diagram would look like. So I'm going to use a dot to represent the block. And I know I'm going to have gravity pulling down. But I also know I have a larger force going up since it is accelerating upward. And since it's being held by a rope, that is going to be a tension force. Okay, so I have my Ft. Now, when I'm looking at how to solve this problem, I look at my net force. Remember, the net force is the sum of all the forces acting on an object. It is equal to mass times acceleration. Well, my mass is going to be 10 kilograms, and my acceleration is 4 meters per second squared, which means my net force is going to be 40 newtons. But I wasn't asking for the net force. I'm trying to figure out what this force of tension is. What is the force of tension in this rope here? So I also have to remember that net force is the sum of the forces. Or in this case, since gravity is pointing downward, the force of the tension minus the force of gravity, since they're opposite. But I'm looking for force of tension, so I need to get it by itself, so I add the force of gravity to either side. Net force plus force of gravity equals the force of tension. But I haven't talked about force of gravity yet. So we have to remember that force is mass times acceleration, and when we're talking about force of gravity, it's going to be the mass times the acceleration due to gravity. So that's going to be 10 times 9.8, which is the acceleration due to gravity, which is going to be 98 newtons. So I can use that and plug that back in over here. So my 40 Newton net force, which I calculated up here, plus my 98 Newton gravitational force is going to equal my force of tension, which happens to be 138 newtons.